Okay, the board is hooked up, so let's fire up Minicom and take a look. I'm going to hit the reset button on the board. There we go. Okay, so the monitor supports a few basic commands like inspect in memory. So we can inspect the start flash here, which is just the vector table. We also call an arbitrary memory address. So I've got a couple of example functions up here. So hidden, which just prints a string out. So we can try that. E39, hidden function called. Perfect. You can also disassemble. So let's do this breakpoint address. And there you go. So we have a couple of NOPs. We got a software breakpoint instruction. Some more NOPs, a wider NOP, and then a return. We can try executing this. And we've now entered the debugger because of the breakpoint instruction. We can exit out of that, and instead of calling, we can call with step, which is the exact same thing, but rather than only invoking the debugger on the breakpoint instruction, we've started at the NOP instead. We can disassemble from here, and we can step through until we hit that breakpoint. One thing you might notice is that certain instructions don't advance the program counter, and breakpoint instructions are a good example. No matter how much we step, it stayed exactly where it is. The program counter has not moved. What we have to do instead is skip over them. So we can use Z for that. And there we are, we're now on to the next knob. We can keep going until the end of the function. Okay. Another thing we can do is we can enter bytes in directly. So let's dump some memory out from SRAM. This is the user area. And now let's enter some bytes there. So 1, 2, 3, 4, 5, 6, 7, 8, AB. And now we can dump that out. And you see here. So we've changed these. The other thing we can enter is instructions. So this is for entering machine code. So I've got some machine code written down that I'm going to enter in. And this is very similar to entering in half words. The only difference is that it's aware of what a wide encoding is. So I'm now going to enter a wide instruction. And you see the moment I enter the first half word, it's going to recognize that. It's going to give me a space so I can enter the next or the second half word of that instruction, rather than moving down onto the next line. And there we go, that's it. So all this does is it just prints the number 42 out. So we can call it. There you go. We can disassemble it. And see what it actually did. Is it moves 2A, which is 42 in hexadecimal, into R0. We then make a system call. So I have two system calls. One allows you to exit, and the other just prints out the contents of R0 onto the screen. We then have this wide NOP, and then we just return. That is all it does. Okay, so let's try assembling a small little function. This is just gonna count from 1 to 10. Something quite simple. So let's assemble into RAM. This is the user area, so this is a free part of memory we can use. You see there's nothing here so far, so we're gonna start with a push. And push R4, and we're also gonna push the link register. Like that. Let's put a couple of knobs, just to give us something to work with. And then we're gonna pop 4, and then rather than popping the link register, we're just gonna pop straight into the program counter instead. And that will be how we return from this function. Let's try calling it, just to make sure that works fine. Oh yeah, it did. We return straight to the assembler. So that's perfect. So I'm going to use R4 to keep track of the count. So I'm going to start off by putting a 1 in there. I'm going to do a move, and into R4 we're going to put that 1. And now what I want is a loop. And then with each iteration of the loop, we're going to add 1 to R4. So this is where I want to start a loop. Let's just label it and call it loop right here. And so I want to compare R4 the immediate of 10, because I want to exit the loop if we get to greater than 10. So I'm going to put a branch here. Go for the condition, we're going to put greater than. Now I don't know where I'm actually branching to just yet, so I'm just going to have it branched to here. That's great. I'm going to skip a couple of nops for later. And now we're going to actually increment R4 here. So we're doing add immediate R4, which is going to be the result of R4 plus the immediate of 1. Okay, and that's it. Now let's actually branch back to our loop. We're going to jump up to this comparison. No condition, we're going to branch to a label, and it's going to be a loop. And there you go. So we start here, and then we're going to hit this branch, and we're going to go back to this compare. We're just going to label this here. That's going to be our ender loop. And now we know where the loop is ending. We're going to go back to this branch and fix it so it jumps to end loop instead. Branch greater than, branch to a label, end loop. Perfect. So let's try that. Okay, so we do our push. Okay, and now we're going to put 1 into R4. So watch this register here. 1. Okay, we're now going to compare it to 10. We're going to jump away if it's greater than, and see from the disassembly. So if this branch doesn't happen, which it shouldn't, we'll hit this knob instead. So I'm going to hit S, step, and there you go, we're in the knob, because 1 is less than 10. Knob, we're going to increment it, so this should become 2, which it does. And now we're going to loop back, do a comparison, add again, and watch it increment. Okay, so it's at 10, and now we're going to add, so it's 11, and now we're back to this comparison. And because this is greater than 10 now, we should jump from here to the end of the loop. We're going to hit this knob and then our pop. So we'll step, we're going to hit this branch, knob, and then we've hit pop, so we've exited the function. Okay, that's great. We have a little function that can count R4 from 1 to 10. Let's actually do something with it. Let's print those numbers out. So if you remember from earlier, there is a system call which will print out the contents of R0. So what we should do is we need to put the value from R4 into R0 and then make the system call. So we can do that with a move. Destination's R0 and the register we want to move into it is R4. And we're going to do S for SVC. Perfect. Let's test that out. Let's go for our loop. We're gonna, here we go. There's our 1 printed out right there. And if we keep going, we have a 2, then a 3, 4, and if we continue, we get the rest of it. If we do a call without stepping, we get our full 1 to 10. We can also call this from outside. And we can also disassemble it. And there you go. There is our program from here to here. Now the monitor can also deal with faults. So you might have seen quite a few times you've had this fix show up. So if I do call and do this, we have warn no fun bit. This is because of the interwork bit, which determines which instruction set we should be using. So on microprocessors this is good because it will allow you to switch between the ARM and the thumb instruction set. But on a microcontroller we only have the thumb one. So calling an address without that bit set is a usage fault, because that would be for ARM, which we don't have. So I can demonstrate this. We're going to do a call, and rather than pressing F for fix, we can hit P for proceed, which will just do it anyway. And there you go, you can see we have a usage fault, which was forced into a hard fault, but that's only because I don't have a separate usage fault handler. But that's fine. and see what the program counter was set to. We can try a few other things, so let's cause a bus fault. I'm going to pick a memory location that isn't actually mapped to anything. Okay, so we got an instruction bus fault. That's because it failed to prefetch. If we were to try and dump memory from there, it would be a different one. Because rather than instruction, we would get a precise data error. And we also have the bus fault address register, which is valid, and has suddenly shown up. Because it's valid, so it will show it to us, rather. Whereas before, it wasn't, so it never appeared. We can also cause a memory fault. That's a bit tricky to do because I don't have the memory protection unit configured. But towards the end of the Cortex's M4's address space is all marked as not executable. So if we were to say call address all Fs, it is an instruction access violation. It is worth pointing out that this isn't a reset. What happens is when we get a hard fault, at the end of it we return back to the monitor, which is different because that way we don't lose any state. You can see if I go to the assembler, I still have that little program I wrote, whereas if I were to reset, so I'm going to hit the reset button, and now I'm going to go back to the assembler, there's nothing there. So it makes it a bit more resilient. If you assemble something and it causes a fault, that's fine, you're not going to lose your work.